In this lecture we're going to look at networks. This is going to take us not quite from as far back as Colossus, but bring us right up to date to World of Warcraft. Today networking is often used for applications like World of Warcraft, massively multi-user online role-playing games where players from all around the world can interact and play with one another pretty much in real time, despite vast differences between where they might actually be logging in from. Networking's also gone very mobile, and we can have satellite navigation apps that also use web information and update themselves from the web while we're out and about, and this is obviously giving us a ubiquitous web and online experience where we can be online and on the internet and networked wherever we are, whenever. It wasn't always like this. Early computers were standalone and there was no communication between different computers, and to be able to use a computer you had to actually be standing next to it pretty much. Development of terminals allowed multiple users, possibly in different locations, to use the same computer at the same time. So a terminal would provide you with, for example, a keyboard and some kind of text output, which could be a screen or it could actually be a line printer. So a lot of early computers, the output, instead of being on a screen or visual display unit, would actually be printed out. Later generations of terminals added graphics and local processing, systems such as the Plato system. To get an idea of these early types of system where users in different rooms in a campus, in different buildings in an institution for example, might all be connected to one computer, you can see a video that's available on YouTube, 1963 Timesharing, a solution to computer bottlenecks. This is an example from MIT. But that was still one computer with access to it from very simple terminals. As we got into the 70s, there was increasing demand to be able to connect to different computers from different locations. ARPANET was a computer network developed to link researchers around the US to the rather limited number of powerful research computers that were available at the time. It wasn't created, as is often said, to create a network that would survive a nuclear attack. That actually relates to some other work that was going on around about the same time in terms of creating a phone network or a communications network that would survive a nuclear attack, and there are some principles they use in common. But what ARPANET did was remove the need to use a separate terminal for each computer, as a single terminal could in principle then connect to any computer that was existing on the network, because you could connect via different computers and nodes. This is a map of the ARPANET network as it was in March 1977, and we can see more or less the geography of the US kind of squared off a little bit, and you can also spot here some network connections over wireless. So there's a simple key here, satellite circuits. So there's a satellite connection to Hawaii, to a computer system at Hawaii, and a satellite network connection to London. Actually also tells you what computers existed at most of these locations, and the common computers on ARPANET at this point were PDP 10s and PDP 11s, a few other systems, DEC systems, and a few others, IBM 360s. And that kind of shows the layout, and you can get some idea of the number of nodes on that network. ARPANET used a system known as packet switching. To explain packet switching, let's first look at what the alternative was, which is circuit switching. Circuit switching is how telephone networks worked. Essentially, when you dialed a number, the network would then create a persistent link from your telephone to the recipient telephone. And for the duration of your call, that one persistent link would be used. If there was a failure in the system, the connection would be broken and the call would fail. So any single node failure breaks the entire link. So for example, if there was a failure at Scottsdale here, then this connection would break. Packet switching does something quite different. It breaks the overall message into small packets. Each packet has information on the destination, and each packet is forwarded from the current node to the next node, and it's sent onwards towards a destination. It's sent one hop at a time across the network to a destination. And the different packets that form a single message may take different routes to the destination. And so we've got two example routes here. And if there's a network failure at one of these nodes that would normally break the connection. Instead, what will happen is the packets will simply be routed through a different node and round the network in a different way. So the data sent in packets, and any large amount of data transferred will be broken up into multiple packets, each one containing the address of the destination and details on who sent that packet. This is the IP number, so it identifies the computer that's sent the packet and that we're trying to get the packet to. A sequence number, so if we've broken up a message into 10 packets, each one will have its own number, 1, 2, 3, 4, 5, 6, and so on. The actual contents of the message, and some extra data at the end that allows you to do error checking to make sure that the data we've received hasn't been corrupted through some kind of noise or other disturbance as it's been transmitted. What you're probably used to working with using the internet is domain names, and here are two examples. In the top we have a web page URL, that's a uniform resource locator, and at the bottom we have an email address. The main part of each of these, though, or the second part in the case of the email address, is the domain name. The domain name is made up of a number of different parts. There's a top level domain. In this case, the .uk, that's a country code. So that's a country code top level domain. If it's something like .com or .net or .org, it's simply known as a top level domain. .ac.uk, well, the AC identifies this as being an academic network, but the AC.uk, well, this is a second level domain, and again this particularly relates to a country code second level domain. UWS identifies University of West of Scotland and is a subdomain. However, uws.ac.uk would normally be packaged or thought of, that you would normally think of that as being a domain name that you might purchase, for example, if you were setting up your own website. So, common domain name might be uws.ac.uk, but the UWS is actually a subdomain of the second level domain. And www.uws.ac.uk is a subdomain of the UWS domain. So there are two different domain names there, and the web page URL, the domain name is www.uws.ac.uk. And the email address, the domain name is uws.ac.uk. Subdomains can be very flexible, so for example, the university could set up a website specific for students, for example, that could be student.uws.ac.uk. Could set up a domain only for staff, and that could be staff.uws.ac.uk, or any other subdomain that they would wish to use. That's the familiar part, but what's going on underneath the hood, so to speak? And this is really a very cursory overview of what's going on inside the networking. There's more details of this in the textbook. And depending which module you're on, which courses you do, in later years you may get a lot more in-depth information on this topic. There are different ways in which we can sort of think about what's going on in the internet. One of the common models that's used to think about this is the OSI 7-layer model. And it basically splits network communications into a set of different layers. At the top we have our applications, so this is any program you might be running, such as World of Warcraft or a web browser. And at the very bottom is the actual physical layer, and the physical layer is the actual wires or the actual wireless connections that are used. So at the very bottom layer we're right down to the actual physical connections that are working. Now if you're using Wi-Fi, for example, there's going to be lots of software there that's required to simply create the wireless link and to manage the data that's being sent over that wireless link. So there's varying data link and network layers that need to work together to be able to send data over that wireless network. Whereas your program that you might write, such as World of Warcraft, doesn't really care about what's going on underneath. It just needs to be able to talk to the World of Warcraft server. If you're using a web browser, it just needs to be able to talk to a web server. It doesn't need to know any of the details about what's going on in the lower levels of the internet. So each layer uses the layer below, but doesn't need to know how it works. So our multi-user game doesn't need to know how the machines are actually physically connected, and my web browser doesn't care whether I'm using Wi-Fi or 3G. That's dealt with by other parts of the networking software and hardware. Now, the most common networking protocols is TCP/IP, which is the Transmission Control Protocol, Internet Protocol. So TCP is a transport layer protocol, and IP is a network layer protocol, which is underneath it, as we can see in this previous slide. So each node on the internet has an IP address, for example. So www.uws.ac.uk has an IP address 146.191.68.100. Now that can actually change over time if the web servers get reconfigured. That's what it is currently. Special servers known as domain name system servers exist to map the domain names that we use to the IP addresses. So the IP addresses are required for the computers to network and communicate to one another, whereas as users and applications, we may find it a lot easier to work in domain names. That's also quite important because it means that we can move a web server from one machine to another machine, and simply by updating the domain name system, we can still get the communications that we want to get. So if they move the UWS web server to a different machine with a different IP address, they could update the domain name system and still get the traffic, and it would still work, hopefully. So here's a very simple example again. If we've got host A and host B, two machines that are trying to communicate, when host A communicates with host B, it might send some traffic, it might go through one router and then another router and be received at host B. What's actually happening underneath the hood is this sort of layered, we can kind of see the simplified layer model, what's going on. So my web browser might communicate with the web server on this machine. And the software as it's written at its level only needs to worry about how that connection is going to work. It's going to use some kind of API or interface that actually connects it to the transport layer. And this thinks about how one host connects to another host. It doesn't deal with any of the problems of the application itself. It doesn't know what the data it's passing means to World of Warcraft or to our web browser, but it handles the host-to-host connections. Below this we have our sort of IP layers, and below this we may have our data link layers, and then at the bottom we've got an actual physical network. So we may have a connection that goes over the Ethernet, connects to a router. The router needs to use the Internet Protocol to work out where to pass on the messages to the next node, to the next router, to then pass on to the host. But as a user or as an application, what we really see or work with is the top diagram here. All this complexity is largely hidden from end users and end applications. To give you a simple example of how complicated it can be in practice, this is me using the Traceroute application on my Windows PC at home to trace the network connections followed and the network nodes followed to go from my machine at home to the university web server about 7 miles away. So to travel this distance of 7 miles physically, my machine connects to a local server, and I'm on the Virgin cable network, and it goes through some local nodes in the Virgin network and actually is sent down the Virgin backbone to Leeds, and is then sent onwards down to London, which is where it joins the JANET, the academic network of the UK. Once it's on the academic network, it's passed back up through, I think, Reading, on to Glasgow, into the ClydeNet, passed on to the Paisley connections on ClydeNet. For some reason it's passed through several machines here at UWS before it finally gets to the UWS web server. So to travel 7 miles physically, my network traffic is actually going to London and back over 20 hops. And this is partly because the combination of the Virgin network, which is what I'm on, and how it is connected into other major networks, in this case the academic network of the UK. And so Virgin and the academic network of the UK, JANET, only seem to meet in London, in this example at least. As well as the internet, we can do networking on a much more small scale or local area, with local area networks. The dominant standard for this is Ethernet. It allows a number of machines, computers, printers, etc. to be connected in a number of different configurations, bus or star being the principal ones. Other devices, hub switches and routers can be used to connect different nodes together. So a bus topology is a fairly straightforward one. All nodes are connected via a single cable. Only one pair of machines can actually communicate at a time, because any signal being sent along the cable will interfere if you try and send another one at the same time. This is called contention, when two or more signals are trying to use the bus at the same time. Only one can actually use a bus at the same time, so there are different algorithms and routines to try and solve this problem. So typically what will happen is if there's contention is detected, both machines will stop and they'll wait a random time period before one of them will try again. And any machine that wants to communicate has to check the network isn't being used currently before it can actually then use the network. Star networks use some kind of hub, router or switch as a central node, which connects all the devices to this single central point. But this hub, router or switch can then in principle allow multiple communications between different devices here, so that any one of these computers can communicate with any other while other pairs of computers are communicating. It also introduces a machine that is a single point of failure, so if this device breaks in the centre, the whole network goes down. We did a quick straw poll in the class, and most people have got some kind of internet connectivity at home, and many people have some kind of network at home as well. So most home and office networks usually connect to the internet via one of three ways. Dial-in or phoning in over a standard phone line using a modem is still used in some areas because it's the only option that's available. It offers very limited bandwidth, so you get very low speeds for downloads and uploads. DSL, digital subscriber line, requires some updated hardware at your telephone exchange, and it allows broadband speeds over standard phone lines. Most DSL lines are asynchronous, supporting much higher download speeds than upload speeds. And this is the principle that you're more likely to want to watch something like a YouTube video. You're going to do that more often than you're going to try and upload a YouTube video. So high speed of access to information is more important than high speed of submitting information to the internet. Cable internet uses cable television infrastructure to provide internet access and is obviously much more limited in terms of geography. You either have cable in your street or you don't, and if you don't have cable access in your street, it's very hard to arrange to get it because it involves digging up the roads and a very expensive process of just laying all the cables. So the current state in the UK is most internet users are on a DSL connection over standard phone lines. A number of users use the cable internet, but some users are still restricted to sort of dial-in. In comparison of DSL versus cable, DSL has very good availability for most of the UK. It uses phone and internet on one connection, and the transmission rate can be affected by a number of factors, including how far you are from the telephone exchange, the actual quality of the phone line cables themselves, and what equipment's installed in your local exchange. And there are very large variances in performance reported for different DSL users, sometimes even for users just in the next street or next building from one another, can report very large variation in performance. Cable internet has relatively limited availability in the UK, offers a separate connection, so you still need a separate phone line. The cable was originally designed for broadcast, and very high use can cause network congestion and contention issues, because the cable system wasn't originally intended for use for, particularly for example, for uploading data. If you've got lots of people playing MMO games or watching YouTube and uploading things as well, then there's a lot of two-way traffic going on, and that's not what the cable network was originally developed for. But you will still typically get higher performance than you would with a DSL connection. But now, of course, a lot of networking nowadays is completely wireless. We don't need to be connected to the wires now for networking. So for Wi-Fi networking, there are various iterations of the IEEE 802.11 standard, which have evolved over years. The N standard is the current version. Wi-Fi networking is commonly built into laptops. Many home devices such as the PlayStation 3 or Nintendo Wii even will have wireless internet access. They do need an access point, so some kind of cable modem or Wi-Fi cable modem or router, typically within 30 to 50 metres, maybe less. And it's worth noting that unencrypted or unprotected Wi-Fi connections can pose a serious security risk. So if you're using Wi-Fi at home, do make sure that you have changed your password and make sure that you have switched on the different encryption and protection systems that are available. Because wireless transmissions can be heard by any listening device, not just the access point, and unencrypted messages can be easily copied. The first common encryption system used for wireless access was WEP, Wired Equivalent Privacy. This is deprecated, that means it's not recommended for use, because it uses one encryption key for all the packets in a message, and so it can be hacked relatively easily. WPA and WPA2, or Wi-Fi Protected Access, uses a different encryption key for every data packet and is a much stronger form of encryption. But sometimes we want to get a bit further away than 30 or 50 metres from a wireless access point, so our home network, for example, wireless access point, still needs connected to the cables that connect us to the internet. If we buy a 3G modem, then we no longer need that. We're now connected to the cell phone, mobile phone network. The early mobile web access was limited by small displays and the very expensive data transfer rates available at the time, and they used systems like WAP and WML, the wireless access protocol and wireless markup language, to provide a very cut down internet interface for mobile phones. Modern mobile internet and third and fourth generation networks, 3G, 3.5G and 4G, which is coming through just now, provide much higher bandwidth and data rates, up to broadband equivalent rates. These are used in things like the iPhone and Android phones and all the latest generations of smartphones, and also used for mobile internet access on laptops and on tablets. I thought it interesting for comparison to just have a wee look at some of the main mobile phone and tablet operating systems. And iOS, for example, is the name of the operating system found on the iPhone and iPad and is produced by Apple. Android is obviously produced by Google and is available on a wide range of handsets by different makers. WebOS used to be from a company called Palm, which have been bought by HP, and HP are now producing their own devices with WebOS on it. Windows Phone 7 is from Microsoft. BlackBerry OS, so BlackBerry have their own operating system, as do Symbian, and Bada is a variant developed by Samsung for some of their devices. and we can compare the features on a wide range of these different phones and operating systems. They all run on ARM processors, and most of them only run currently on ARM processors. And we've got whether they allow you to develop on different machines. So to develop for the iPhone or iPad, you need to use a Mac, and to develop on a Windows phone, you need to use a Windows machine. The main application, in very broad sense, that people use on the internet these days, and the one that brought it into the people's homes, was the World Wide Web. Now, once upon a time, finding documents or resources on the internet was not always easy. It often required a very detailed knowledge of what computers were actually available and where particular information was likely to be held. So if you wanted to find a particular piece of information, you might actually need to know what computer it was on, and how to connect to that computer, and a lot of detailed knowledge simply to get the information that you're looking for. In 1989, Tim Berners-Lee proposed a hypertext-based information sharing system for the internet. Now, hypertext already existed. This is kind of text documents where you've got some forms of links between different documents, and so you could be in one document or one page, click on a link and be taken to another page. Hypertext already existed, but not really networked in this way. So for example, through apps on like HyperCard on Macs. When interviewed for the Virtual Revolution, Tim Berners-Lee really explains why he invented the World Wide Web, and there's a link to a video that's well worth watching. But basically, Tim Berners-Lee says he invented the web because it was so frustrating it didn't exist. He was working at CERN, where he needed to get information about different systems that different people were using and document and write up about those systems, and it was frustrating because there was no easy way of getting the information from all these different systems and getting access to all of it. He spent a lot of his time just talking to people to find out this information, and he thought it would be much easier if it was able to access it from one computer, from one terminal, just to be able to access information on any system. And the problem was a lack of a common standard documentation system that allowed links between documents. And importantly, even allowing links between documents where your documents are on different systems altogether. So we can have a document on my computer and it can link to a document on your computer. And that was a really important need for where he was working at CERN in particular, where there were people from different universities from all over the world and different companies from all over the world were trying to work together, and they all had their own systems. As a very brief history of the web, the very first web server went live in 1990. In 1993, the first graphical browser for the Macs and PCs was available, rather than Macs or PCs. By 1995, the World Wide Web was starting to become a bit more widespread, but still hadn't really reached into homes particularly. Indeed, the first edition of Bill Gates' book, The Road Ahead, doesn't really mention the web at all. But by the end of 1995, the World Wide Web was starting to get a lot more attention. But today we now have this situation where we have a ubiquitous web. Almost wherever we go we have access to the web, and the web is used for everything. We want to book flights, we use the web. We want to buy books, we use the web. We can do grocery shopping on the web. So the web's reached into almost every area of people's lives and is available almost anywhere we go. Just to reaffirm some of the common web terms, so some of these you might type in a lot and you might not have realised what they meant. HTTP, Hypertext Transport Protocol. So that's a particular protocol language used by browsers and servers to ask for content and to provide pages. HTML is the Hypertext Markup Language, and that's a markup language used for writing web pages. So we can say we want to create a heading, we want to create a paragraph of text, we want to emphasize a piece of text, make it bold, for example. URL is the Universal Resource Locator. I called it uniform earlier, it's actually Universal Resource Locator. Each document or resource on the internet can have a unique URL that anyone can use to access that file. And the web brought the internet into daily life and ordinary homes. So prior to the web, the internet was quite hard to use, really. You had to know a lot about the different computers you were connecting to. The web made it easy to use, and after the web, more and more useful features for ordinary people became available on the internet, and it allowed the internet to become part of people's daily lives in ordinary homes. And it's all through increased access to information and services. But later generations of applications focus less on giving users access to information and much more emphasis on letting users create their own. Blogs, wikis, social networks, YouTube and so on allow people to create content and share content and access content used by others. And this is sometimes called Web 2.0, sometimes called the read-write web. Over the internet, there's a few other key types of applications that exist and ways in which users communicate to each other and with other machines. And the standard ways in which we're connecting, if we're, for example, playing World of Warcraft or viewing a web page, we're usually in a client-server connection. We are the client, we are asking for information, and the World of Warcraft server, the world we're logging into, or the web server we're connecting to and getting information from, is a server. So one machine in the internet is a server, and one or more machines can be clients. And this works for chat or instant messaging, many multi-user games, MMO games particularly. Other form of connection on the internet is a more even form where machines connect to each other as peers, and it's peer-to-peer networking. This was made really infamous by Napster and illegal file sharing, but there's many other uses of peer-to-peer networking. Many peer-to-peer applications use a subset of peers to act as a directory. So for example, if we're using Skype supernodes, and if this was a supernode here, this might be acting as a directory that other peers can connect to find information about how to find or connect to different nodes in the network. So many peer-to-peer apps do use a subset of the whole set of peers as directories, and that allows any other client to access, identify resources or find out where other peers are. So when we want to make a Skype call to another user, our machine can work out how to connect to that user, or when we're using BitTorrent, peers can be providers of files and also trackers, the directories that are allowing people to find where files are stored. Some applications also maintain a client-server distinction but have networks of servers. So the servers, instead of all existing in one building or in one location, can actually be spread across the world. One example of this, and this is a sort of 3D virtual world example, is the OpenSim Hypergrid. OpenSim is this open source 3D virtual world platform, and anyone can run a server, can create their own small virtual world, but you can also connect your virtual world to this hypergrid that allows connections between my virtual world and your virtual world, and creates this hypergrid of virtual worlds. There's much more you can read in this. Wikipedia, as usual, has got lots and lots of material. History of the Internet, TCP/IP, DSL, history of the World Wide Web, and so on. Principles of Computer Hardware, Chapter 14 is on computer communications. The Virtual Revolution series in BBC, there are more clips you can see online, and there's a lot more interesting stuff there. Well worth some time viewing. And credits for the images used as usual. That's all for now. Thank you.